doing this. Okay, good evening and thank you all for coming. There will be other two speakers after me. They will also talk about the scientific aspects of music and sound in general. But being from Raman Research Institute, I thought I will talk about some of Raman's work on sound waves. He has done a lot of things, but I picked up a few things. If you look at Raman's work, I mean, we know about Raman effect, but that's something to do with light. But if you look at his work throughout his career, there's one theme that runs across his work, apart from other things, and that's the waves. The sound is a kind of wave, so is light. And he was, in general, curious and very fascinated by the wave phenomena, the different subtle effects of waves. And one of the things that he was interested in is the whispering gallery. I'm sure you have heard about some of the architectural structures. For example, we have in Karnataka, in Bijapur, Gol Gumbaz, and this is a picture of that, and this is Victoria Memorial in Calcutta. This is also a picture of the inside. And one of the most famous examples is in London, St. Paul's Cathedral. So basically, there's a circular rim kind of a structure, and if you whisper at one place, you can hear the sound even if you're standing, very far away on the opposite corner, and not just one corner, but along the rim. But I should warn you here, if you Google whispering galleries and the scientific explanation, you might actually end up listening to the wrong explanation. There are some YouTube videos which give the wrong explanation, and they say that there are two foci, the focus, okay, and if you whisper at one of the foci, then it gets focused into another foci. But that's not the case. It actually can be heard all along the rim. So it's not just a question of two centers. So those explanations, although there are lots of information in the internet these days, one has to be very careful about what you get. And so now this is one of the papers that Raman, this is the first page of Raman's work in 1922. So he mentions Gol Gumbaz and Victoria Memorial. Also there's a structure in Patna, the granary, the old granary, which is also like a dome-like structure. And he goes into the architectural, the dimensional details of all these structures. Now, there was an explanation at that time when he wrote this article in 1922. There was an explanation going back to Lord Rayleigh. Lord Rayleigh, those of you who have studied physics, a lot of things about waves that we know go back to Lord Rayleigh. Okay, and so Lord Rayleigh gave an explanation in 1878, but Raman had found some problems with the explanation because he did some experiments in London, in St. Paul's Cathedral, also here in Gol Gumbaz and in Victoria Memorial, where he found that there's some discrepancies there, and he was not quite satisfactory. And so he set out to find out the real reasons. Now, to understand what's happening, one has to think of waves in general. It can be water waves also. So suppose you take a bathtub and you make a partition, make it into divide it into two halves, and make a hole in the partition, excite some water waves by doing something, disturb the water waves and create ripples there. And if you inspect what's happening on how the waves go through the hole and how it goes into the other half, you'll notice that they can spread out. In scientific jargon, we call it waves can diffract. Okay, I'm not going to use any jargon, so those who are scientists here and the science students can pardon me for not being precise enough. So I'll just say that they spread around. Okay, and the amount of spreading, the angle by which they can spread, depends on two things. One is the size of the hole and the wavelength of the whatever waves you are exciting. If this ratio If the size of the hole is small compared to the wavelength, then the waves are going to spread out a lot. So, as you can see here, so they're going to spread out. Okay. Now, for light in general, the wavelength is very small. This wavelength is very small compared to the typical hole sizes of objects that we encounter in daily life, which means that this ratio is very large. If denominator is small, the ratio is going to be large, and so it is not going to spread out, and this is why we are taught that light travels in a straight line. It doesn't spread out much. But sound wave, but if you can make a hole which is small enough comparable to the wavelength, then you can see the wave effect, the diffraction effect of light also. But this is usually seen in, for example, sound. For sound waves, the wavelengths are comparable to the sizes of apertures, the size of a door or window, and so you can see then the waves can bend around, they can spread, which is why if somebody is whispering or saying something behind me, I can hear. Whereas if somebody shines a light, I won't be able to see, right? It will not want to pass through me. It's not going to bend around me. So, but then when you whisper, the frequencies that you excite, it's such that the wavelength is of the order of a few centimeters. Okay, that depends on the speed of sound in the air. But the bottom line is that when you whisper, then the wavelength is of the order of a few centimeters, which is comparable to the size of our mouth aperture, which is why it doesn't spread around much. Okay, so when somebody whispers behind you, you can't really hear, but if somebody speaks loudly, then you can hear, because the waves can bend around. Now, so when we speak loud, then the wavelength can become 10 times larger, or the frequency is smaller, and so you can hear them. Now, what Rayleigh thought was happening is that when you whisper at a point, then the sound waves is confined. Okay, it's not spreading around. It doesn't spread. It's confined to a small cone. Okay, and those waves can repeatedly get reflected and then can come back, and you can hear at different places. Okay, that's what the explanation by Rayleigh. And he thought that the whispers can become trapped along in a layer close to the wall. And in 1910, then he did this again, and he compared to the effect of vibration of a circular membrane. He was working on the mathematical description of what happens in a circular membrane. We'll come back to this later in another context. This is, by the way, one of the best articles that you can read on whispering galleries in Scientific American, going back to 1978 by Joel Walker. So, the Resnick Halliday has a third author now, Joel Walker, who used to write a fascinating series called Amateur Scientist. And this also talks about how one can do some experiments, simple devices in. So, you can read that. And so, what Raman found is that the intensity of sound along the ring is not constant, as Rayleigh had predicted. There are places where the intensity is large, where the places where the intensity is small, and they alternate. This is what he found, and that is so he thought that there's something else is happening there. He came back to India. He had a student named Bidubhushan Ray in Calcutta, and he asked his student to do an optical analog. Sound waves, he can do the light is also a wave, so you can build a whispering gallery for where light can whisper, right? So Bidubhushan Ray actually did that in an experiment. This paper came out in 1922 in Bulletins of Calcutta Mathematical Society. It's very hard to find these days anyway, but internet has everything now. So what they found is that there are places, alternate places with darkness and light, similar to what Raman had found for sound. There are alternate places where you can hear and not hear, hear and not hear. So this is sort of visual description of what is happening. So what Raman then found is that they are getting reflected, the sound waves are getting reflected from different places, but the reflected rays, so these two waves, when they come to some, arrive at another point, they can either add up or they can cancel one another, okay, depending on the geometry and where you are, okay. So it's called the interference. I mean, you can either add the waves or you can cancel out the effects of the waves, right? So this is what, and this is the paper that he wrote in Nature, the letter to Nature. And right now, interestingly, the story doesn't end here. Raman was also interested in other things, among other, I mean, like natural phenomena. He was probably one of the last, what you call the, natural philosophers, curious about what's happening in nature. So he was also interested in pearls, in gems and other things. Pearl is very interesting. Pearl has layers of small crystals and is stratified. And so he had written papers on structures of pearls. Now it turns out that many years later, from my institute, Raman Research Institute, it was later shown that the pearl shines in a unique manner, just like it's like an optical analog of whispering gallery. It's light getting scattered in different along the layer. So when you shine a pearl from say at one spot here, the light it's not dark everywhere else. You can also see the illumination there, and that gives the pearl its unique so this is the optical counterpart of the acoustic whispering gallery effect, and this paper came out. This is in 1990s, late 1990s, from Raman Research Institute. And whispering gallery, as I said, this is a wave phenomena, and any different kinds of waves would will show this effect. Even earthquakes. So sometimes earthquakes, there are waves, and you can think of the whole earth as a whispering gallery. And it has happened, for example, 1960, a strong earthquake in Chile. Apparently, the effect was seen, felt around the globe for about 3-4 days, and there were intensities going up and down within a span of few hours. So maybe this interference effect in different places was happening there. We now, astronomers now see these sort of effects in stars. This is it's a theoretical picture of what's happening in the sun. So this is like sun quakes. Same, it's like a whispering gallery effect. Okay. Now engineers use these effects to detect defects where it's very difficult to identify some of the defects. For example, there's this interesting story about US Air Force C-141 in 1990s. They developed a snag. Maybe some hole in the wings had some defect. It was very difficult to find where the defect was. So what they did, they excited some waves and then found whether there is an interference pattern along the rim, and that was very easy to find out where the defect was. So now whispering gallery is being used by engineers as a sort of a sensor. Okay, this is a very interesting article that you can look up. This is in Physics World. And this talks about all these phenomena. So it's out in, it's written for general public. And do I have 5 minutes? So to end with, I just thought I'll talk about Raman and his the tabla that you have seen in the exhibition. And you must have seen the sand, the small particles, grains that they have put in there to excite different modes. So Raman was also interested in sound and the difference between the uniqueness of Indian instruments, and he set out to find out what sets Indian, say, percussion instruments like tabla, mridangam, different from the Western drum. And so in one of his papers, in the introduction, he writes that all the instruments of percussion known to European science are thus essentially non-musical and can be tolerated in open air music or in large orchestras where a little noise more or less makes no difference. Indian musical instruments of percussion, however, stand in an entirely different category in its tonal qualities. And he wanted to find out what they are. So, so he worked on tabla, mridangam. So as you know, in a string, right, one can, if you pluck a string, you can excite different kinds of vibrations, different patterns of vibration. So one is the fundamental mode, but you can also excite these, what are called the harmonics, right? Those are also going to be excited in different proportions, which will create different timbres, like timbre, right, of the tonal quality of the sound. So Just like that, in a circular membrane, like the tabla, the drum head, you can also excite different modes. Interestingly, so again, we have to, Lord Rayleigh had his explanations, just like the whispering gallery thing. So this is a picture of the different, different modes of vibration that you can excite in a circular ring. Okay, these are the nodal circles where the effect is, so these are nodes. Okay, these are nodes where it's not moving, and these are the antinodes where the amplitude is maximum. Okay, so so these are the different nodal circles. I mean, so you can excite all these things, and these are the frequencies in relation to the fundamental mode. Interestingly, as you will see that the frequency ratio is not integral, in the sense that if I take the ratio of this to this, it's 1.594 to 1. 1.594 cannot be written as a rational ratio of integral multiples. And that makes it very non-musical, because we know that, if you want to, if a sound has to appeal musically to our ear, the frequencies have to have an integral ratio. For example, sa and pa, the frequencies have a ratio of 3 to 2, 2 to 3. Okay, or sa and re, for example, it's the other way around, 8 to 9. Okay, sa and ga, it's 64 to 81. That sounds better, musical, and some aesthetical appeal in our ear. And if you don't have this integral ratios of different modes, because you're exciting different modes of vibration, it's not going to sound very musical, which is what Raman had figured out. The Western drums, they sound very non-musical. And you put this, what's called the siyahi there, right? The loaded in Indian tabla or mridangam, and this loading is done very, very carefully in a manner that, so these are the modes, 6 modes of with the fundamental that Raman had excited, and he goes into great detail explaining how the different modes can be excited, and he puts the sand grains right after exciting them and showing that. So, and these have the integral ratios, and so they sound very musical. They have they appealing to us. And there are lots of details about, for example, tabla and mridangam, you have this ring there, right? What are the effects of that? And in the left hand side of the tabla or mridangam, right, the loading is not in the center, it's slightly off center. That also has an effect. And he talks about all this. Then he talks about, for example, what's the difference between guitar and veena. So in guitar, for example, this is the structure of the bridge. In guitar, it's almost like a very sharp blade, where in veena, it gradually tapers off. So the string is like a tangent at some point to the bridge. That he sort of conjectured. He never came back to this later with any greater detailed work, but he said that there's probably a transfer of energy when you pluck a string there. It's transferring some energy to the bridge, and the bridge is this transferring energy back to the string later on and exciting other harmonics, which makes it very rich in the tonal qualities. So yeah, I'll stop here. So this is, some glimpses of Raman's work on Indian instruments and sound in general. So this, by the way, this work on the Whispering Gallery, the optical analog of Whispering Gallery, that was his first work with light. After that,